Okay, now we will talking about the difference between PVD and CVD of molybdenum disulfide. And this is a more outline. And this and other layer-dependent band structure variation in TMDCS has recently seen increased research interest, particularly their option and optoelectric properties. For instance, as a result of the direct bandgap, photon with energy greater than the bandgap can be easily absorbed. Hence, there is an upward change in the photoluminescence absorption and photoconductivity spectra for ultra-field MOS2, especially for monolayer MOS2. This phenomena along the possibility of using MOS2 for optoelectric applications. First, I would like to introduce the structure of MOS2. MOS2 is a typical precision metal dichrogenate materials. It consists of S2 MOS, MO2S layer that are strong bonding by a covalent interactions, while the layer themselves are held together by weak van der Waals force between sulfur atoms. Because of this weak interlayer bonding, free layer or even monolayer MOS2 can be easily obtained through simple methods such as chemical exfoliation. In most studies, MOS2 is found in a hexagonal crystal structure. Also, graphene exhibits excellent electric and thermal conductivity. Its lack of a bandgap significantly limits its application in low power electro switch and logic device. In contrast, bulk MOS2 is a semiconductor with an indirect bandgap of approximately 1 eV. As the number of layers decreases, its electron structure changes, and the indirect bandgap of bulk MOS2 is transformed into a direct bandgap approximately 1.8 eV in monolayer MOS2. Monolayer MOS2 possesses a direct bandgap of approximately 1.8 eV, which makes it highly suitable for nanoscreen switch devices such as field effect transistor and memory device. Many studies have demonstrated that MOS2 can achieve a high on and off current rate along with low leakage current, making it a promising candidate for next generation electrode applications. In the field of optoelectrode, MOS2 also show great potential due to its strong absorption in the solar spectrum. It can efficiently convert light into electrical signal or energy. As a result, MOS2 has been well obtained in photo detector and solar cell. Furthermore, in energy-related application, the structure of MOS2 provides active seed that can effectively promote hydrogen generation, make it a suitable electric catalyst for the HER. In the lithium and ion buttons, MOS2 can also serve as an electron material, offer good electrochemical performance and cyclic stability. Importantly, the properties of MOS2 are highly dependent on the number of layers. Therefore, the fabrication of thin and well-controlled MOS2 field is critical step in device relations.
Hi, this diagram illustrates how PVD stack materials onto a substrate at low temperature through physical bender. Left, first part. You can see that within the vacuum chamber, argon ions are attracted by a magnetic field to bamboo, lay, molybdenum, MOS2, and targets, sputtering out atom catalyst. Part 2 and center part. The resulting thin film are typically thicker and inhabit a concurrent grain structure, microscopic when subject to lateral force. These layers slide easily against each other, provide a replicating effect. Part 3 is right part. Coating on dry bits or bearings enhancing its mechanical properties of wearing resist and low corrosion. And this diagram demonstrates how CVD grows perfect atomic thin crystal on a substrate through gas phase chemical reaction at extremely high temperatures. First part, this shows a high temperature top furnace, upstream sulfur powder, and central margin tech oxygen. Upstream power are heat to beverage, guided by a carrying gas. They rest on the surface of a high temperature substrate, such as SiO2, downstream. Part 2, the resulting material is no longer as a thin coating, but monolayer triangulating single crystal demos. The diagram highlights a clear physical transition. The shift from an indirect band gap to a direct band gap, which grows the material inhibition both photonescence capillary. Part 3 show a monolayer MOS2 corrupting into an atomically thin film effect transistor switch implies its electric transport properties. PVD key advantage. This one is PVD vs CVD. Material position. PVD is industrial grade laboratory or pneumatic coating. CVD is number K electric and optometric materials. Advantage like PVD, low temperature process, excellent adhesion, easy sink control, environment friendly. And CVD is high quality crystallization and unit shape prevention, atomic level thickness, and large error universe. And disadvantage of PVD. PVD poor stack coverage, low crystalline, and high cost of materials. CVD is high temperature elimination, complex process, chemical risks, and slow production rate. For core feature, PVD is high hardness, low confinement of friction, concurrent crystal structure. CVD is high electron mobility, direct band gap and photoelement sense. Application of PVD is can aerospace, bearings, coating tools, or presentation models. Yeah, CVD is next generation transistor, photo sensors, or hydrogen catalyst. And conclusion, the despite difference between microstructure and dimensions, and when PVD operates on a stack logic, is producing thing with calculable crystalline structure. Its physical property stem from the slide of fence there workflows between layers, with a focus on microstructure, mechanical potential, and soil lubrication. And CVD follows a growing logic. It products same thing with single crystal demo structure. Its physical property origin from change in the band structure under quantum confinement effects, with a focus on atomic level electric switch and photoelectric reaction, and component of environment adaptability and application sensors. One is the advantage of PVD process lies in the versatility. Because of its low temperature and high speed, it can be easily applied to extend industrial metal substrate, and making it the best solution to improve the lifespan of mechanical parts. CVD process lies in extremely performer. The advantage of CVD is although the process conditions are harsh, it can provide the high mobility and transitional that the semiconductor industry needs most at present, and is a key material for future process below 2 nanometer. Although the process condition, yes. This is our reference. Thank you, listening.